Today we are going to learn about simplify models with pruning techniques. We will explore how to reduce model size and increase efficiency by implementing various pruning methods, focusing on their impact in resource-constrained environments. Welcome to our session on model pruning. In this video, we will explore the significance of pruning in machine learning. Model pruning is a technique used to reduce the size of neural networks by eliminating unnecessary weights, making them more efficient for deployment, especially in environments with limited resources. By understanding and applying pruning techniques, you can ensure that your models maintain performance while becoming more compact and faster. This process is crucial for deploying models on edge devices or in situations where computational resources are limited.
Model pruning is vital in the modern machine learning landscape due to its ability to enhance the efficiency of neural networks. By intelligently removing redundant or less important weights from a model, pruning can significantly reduce the model's size and computational requirements. This reduction is critical for deploying models on devices with limited processing power, such as smartphones or IoT devices. Moreover, pruning helps in optimizing resource usage, which is important for large-scale deployments where computational and storage resources are at a premium. Importantly, well-executed pruning maintains the model's accuracy, ensuring that the model's predictions remain reliable. Thus, pruning not only contributes to reduced resource consumption but also facilitates smoother and faster deployment across various platforms. Pruning can be categorized into two main types: unstructured and structured pruning. Unstructured pruning involves removing individual weights in a neural network that are deemed unnecessary, without considering their position within the network structure. This type of pruning can lead to a smaller model size but might result in irregular memory access patterns, which can be inefficient on certain hardware. On the other hand, structured pruning removes entire neurons, filters, or channels, maintaining the geometric integrity of the layers. This method is more hardware-friendly and can lead to more significant speedups, especially on GPUs. Each type of pruning has its advantages and best use cases, and the choice between them depends on the specific requirements of the deployment environment and the model architecture.
Identifying redundant weights is a crucial step in the pruning process. It involves evaluating the importance of each weight in the network and determining which can be removed without significantly impacting the model's performance. One common method is setting a threshold for weight magnitude, where weights below this threshold are considered candidates for pruning. Alternatively, data-driven approaches such as analyzing the impact of weights on validation accuracy can also be used to identify less critical weights. An iterative process, where weights are pruned and the model is retrained multiple times, can help in fine-tuning the pruning process, ensuring that only truly redundant weights are removed. This iterative approach helps in maintaining model performance while achieving the desired reduction in size. Implementing weight pruning involves several steps, starting with setting clear objectives for what you want to achieve, such as a specific reduction in model size or an improvement in inference speed. Next, choose a pruning strategy that aligns with your objectives, whether it's unstructured or structured pruning. The actual pruning process involves using algorithms or frameworks that can identify and remove redundant weights. Once pruning is complete, retraining the pruned model is essential to recover any lost accuracy and to fine-tune the remaining weights. Finally, evaluate the performance of the pruned model to ensure it meets the desired objectives without significant loss in accuracy. This step-by-step approach ensures that pruning is done systematically and effectively, leading to better deployment outcomes. Pruning involves inherent trade-offs between reducing model size and maintaining accuracy. Understanding these trade-offs is crucial for making informed decisions. Reducing model size can lead to faster inference times and lower resource consumption, but it might also affect the model's accuracy if not done carefully. It's essential to balance these priorities based on the specific use case and deployment environment. Evaluating performance metrics such as inference speed, memory usage, and accuracy can help in assessing the impact of pruning. Additionally, optimization strategies such as layer-wise pruning or adaptive pruning can be employed to find the right balance, ensuring that the pruned model delivers the desired performance without compromising accuracy. Several tools and libraries are available to automate the pruning process, making it easier for practitioners to implement pruning in their machine learning workflows. Popular libraries such as TensorFlow Model Optimization Toolkit, PyTorch's Torch Vision, and others offer built-in functionalities for pruning models. These tools provide ease of use and seamless integration with existing machine learning frameworks, allowing for efficient pruning implementations. Additionally, these libraries come with extensive community support, offering resources, tutorials, and forums to help users navigate the pruning process. Leveraging these tools can significantly reduce the complexity and time required to implement pruning, enabling practitioners to focus on optimizing their models for deployment. Examining real-world case studies of successful pruning implementations provides valuable insights into the practical applications and benefits of pruning. For instance, tech companies have used pruning to deploy large language models on mobile devices, achieving significant reductions in model size while maintaining performance. In another case, a company in the healthcare industry used pruning to optimize image recognition models for medical diagnostics, improving inference speed and reducing resource consumption. These case studies highlight the performance improvements achieved through pruning, as well as the challenges faced during implementation, such as maintaining accuracy and optimizing resource usage. By learning from these examples, practitioners can better understand how to apply pruning techniques effectively in their own projects.
The field of model pruning continues to evolve, with emerging techniques and advancements shaping its future. Researchers are exploring new methods such as dynamic pruning, which adapts the pruning process during model inference based on input data characteristics. Additionally, advancements in AI and machine learning are driving the development of more sophisticated pruning algorithms that can automatically optimize models for specific tasks and environments. Future research directions focus on improving the scalability and efficiency of pruning methods, as well as integrating pruning with other optimization techniques like quantization and distillation. These advancements have the potential to significantly impact the industry, enabling more efficient deployment of machine learning models across a wide range of applications.
In conclusion, model pruning is a powerful technique for simplifying machine learning models, enhancing their efficiency, and optimizing resource usage. Throughout this video, we've explored the significance of pruning, different types of pruning methods, and how to implement and evaluate them. We've also looked at real-world case studies and future trends shaping the field. Pruning is increasingly important as it enables the deployment of complex models on resource-constrained devices without sacrificing accuracy. We encourage you to continue exploring pruning techniques and leverage them in your own projects to achieve efficient and scalable machine learning solutions. Thank you for joining us today.